Morning again to everyone who have joined and who are joining, and welcome all. Today we are talking about different methods to calculate diversity of loads, which has been traditionally done by all the distribution networks planning people. The thing which we will be highlighting is what are the new challenges, why this topic has come up again to our attention. That diversity will determine the demand at a given point, and the demand will be used for the network design. That means sizing the cables, sizing the transformer, the protection devices, and also these days to know the hosting capacity, to know the import-export limits. So, and in this uh, webinar today, uh, let me introduce the panel. My name is Yogendra, and I'm from EA Technology, Australia. And with me, the three colleagues from EA Technology UK are joining, and I know it's very late evening for them. Catherine, uh, David Mills, and Ian Cooper. And all three are actually joining this webinar from UK, and you will hear from them now, especially about the debut method, how that can take care of current requirements and the future challenges in calculating the diversity and ultimately the demand. Next slide, please. We have just started. Again, welcome everyone who have joined now. We've just started a minute before, and I was saying that we are here, and I'm joined with the three colleagues from UK for this webinar. I'm actually just setting the scene and saying, I mean, look, every planning engineer, it is their bread and butter to calculate the ADMD and the demand and forecasting. So what is new? So basically, these figures, all these figures are from draft AIMO. AIMO produces ISP, so this is from ISP 2024 draft. And in the first figure, if you see the distribution side, the solar PV, the roof, the electric vehicles, and battery storage are the three new, variations or three new, challenges of DER, distributed energy resources. They are also called CER, consumer energy resources, depending on, they are owned by consumer and it's a less, smaller in sizes. But whether we call DER or CER, these are the new entrants. Now, the picture in the middle is saying that because of the net zero transition, the electrification of transport, electrification of all the processes, cooking, will actually make this demand and make it necessary for the capacity, gigawatt capacity, to jump even 2-3 times, which is seen in this picture in the middle. And it is saying, but that will not be coming from the coal, the traditional sources. That will all be coming from renewable energy sources. But if you see the purple line there, it says it is actually, it is the coordinated CER, the purple one. That is the coordinated CER or DER include the battery storage and electric vehicles going forward. So that means we are saying there's a big portion coming from managing the batteries and electric vehicles, because both of them can be a load, or both of them can be a source of generation, depending on the usage. So this is the new thing. And the pictures on the right, I want to highlight in this thing is that, yes, the total throughput of energy in terawatt hours is going to increase many folds, but it also shows that that requirement of electric vehicles will be offset or met by the rooftop solar. So that is where this complexity will come. How much will be met by rooftop solar? What will be the net effect on the demand? So that is what we will be discussing. The next slide, please. Look, again, I'm emphasizing this is not Australia's problem. This is global problem. And in our region, the New Zealand is actually expecting the same thing, the vehicle electrification and process heat to increase the demand. Next slide, please. And electric vehicle is highlighted in the sense because that is now unstoppable, that is coming globally, and basically how we place the EV chargers where the capacity is available. And when do we charge the EVs when the capacity is available? So these sort of arrangements will also decide, will be dependent on the diversity we see in these loads. Now I will hand over to Catherine now.
Thanks, Yukendra. Good morning, everyone. I'll be talking you through debut and how it can be used to, it's a statistical approach to modeling diversity and network demand at low voltages. So to start with, let's take a look at what demand looks like. So if you hook up a measurement of power to any random house on any random day, it might look something a little bit like this. And you can see immediately that this is really unpredictable, it's really random, and you really don't want to be basing your models of the network around something so hard to work with. So this is where the concept of diversity comes in. And diversity is essentially the expected variation in demand between similar customers. For example, domestic demand can vary quite a lot as people have different types and sizes of all sorts of different appliances, and they use them at different times of day, or often on some days, but not others. And this really affects the expected maximum demand of a house or houses. So taking a UK house for illustration, the maximum demand is typically the winter evening. When people have come home from work, they put their oven and their hobs on, all sorts of chargers, devices, etc. And this maximum demand for a UK house tends to be about 10 to 15 kilowatts. But what do you do if you have an entire street? If you've got all sorts, so many dozens or hundreds of houses that are all doing this? You don't want to use this 10 to 15 kilowatts for each house because it's not going to be doing that very often. And all houses certainly aren't going to be doing that at exactly the same time of day regularly. So how do we model what the network is actually likely to experience? So a traditional way to do this is through after diversity maximum demand. And this isn't a specific method, it's more a way of estimating expected maximum demand after you've accounted for the effects of diversity for a property type. Now, different network operators all across the world use slightly different methods. Some are fast and simple, some are more complicated, but perhaps a little bit more accurate. So perhaps the most common method is using a flat ADMD per customer, just a flat kilowatt or kVA value for each type of property. So for example, for a UK house, this could be 2 to 3 kilowatts. For an Australian house, this could be 5 or 6 kilowatts. And different property types have different ADMDs assigned. A variant of this, shown by the second equation, is similar. It allows a flat kilowatt per customer, A times N, plus a floor level P, which is used to account for the extra service cable demand at low customer numbers. And this produces a curved line, the orange line on the graph for a typical UK size house. Other network operators, you do tend to get some empirically determined methods, so taking a large amount of data and determining a method of a graph, a behavior for that property type from the data. And an example given is you fit an exponential curve to the ADMD per customer graph. This is the green line shown. And all of these different methods have their various pros and cons. For example, flat method, flat kilowatt per customer, is really fast. It's really easy to estimate demands, currents, and volt drops using this flat demand. However, it does come with a major drawback of being inaccurate because you're forced to choose a single value for the customer, it's either going to be inaccurate at low customer numbers or at, so on your service cable, for example, or if you pick a higher value, it's going to overestimate your demand at transformers or mains cables where you've got a lot of customers. Alternatively, developing custom methods like fitting data to graphs empirically means you've got to come up with continually updated methods that you need to create custom tools and spreadsheets for. So this isn't ideal either. So this is where DEBU as an approach comes in. DEBU is a method for estimating diversity and low voltage demand. It adapts the demand it models for different customer numbers all the way across a network, and this enables the right amount of demand to be modeled at each point in the network, and therefore the right amount of demand to be connected at each point in the network. Every network has its low customer number sections, as every network has service cables, and it's important to model these accurately too, not just the transformers and first legs of the network. So what is DEBU? Well, DEBU is based on a report called the Association of Chief Engineers Report 49, or ACE 49 for short. This was developed in the early 1980s, but it's been proven based on data that it's still relevant today for modeling networks. It's been widely used by network operators across the UK for the best part of this 40-odd years. And it's been widely held as reliable. It produces well-designed networks that aren't really over-engineered, and they aren't blowing up all the time. So DEBU is a statistical approach. It's based on the observation that customer demand during a half-hour slot is approximately normally distributed, and you can do a lot with the statistics from this. So in the DEBU approach, each customer's half hour of demand is modelled separately using a mean and a variable component of demand. And this allows modelling of a diversity as well as the coincidence of times of maximum demand as well. Typically, the 90th percentile demand is used as the design demand for a network. This is essentially a realistic worst case scenario. It's something the network's actually likely to see during its lifetime, during a particularly bad stormy cold winter, for example. But it's not a design demand that's large enough that the network is over-engineered and really expensive. It's a really nice balance between this cost and overload risk. DEBU's major benefit is, as I mentioned, how it models diversity. It's the dynamic approach models different demands at different sections of the network. So on a cable that's got one customer on it, on the service cable, you've got a one customer level of diversity. Further up the network, you've got, with many customers, you're approaching the far end of the ADMD per customer curve, and you're getting this lower equivalent per customer. So how do you model a network using the DEBU approach? So you do require a specialized tool to model networks in the DEBU approach, and this tool is called VisNet Design. It's EO Technologies' network design and load flow software. It's a web-based tool with a really quick and easy modeling approach. And I'll just set the video going so you can just see a little bit of an example of VisNet Design. So you can either draw a network from scratch using the drawing tools up in the top left. You can design transformers and set their various properties, such as their number of connected phases and their size in kVA. You can set different sorts of conductors, overhead lines, underground cables, and nodes for joints and link boxes. And again, you can configure various properties, so your cables are representing the right impedance across the network, and then whether they're mains and service and so forth. And finally, we've got a variety of different customer models available in the tool as well, domestic, commercial, industrial, and you can set all sorts of properties for these as well. So, for example, for domestic properties, there's gas heated, electric heated, various sizes, and you can configure these to a particular scale based on an estimated annual consumption or a known maximum demand. And you can also add subgroups, which are related properties. So, for example, adding an EV charger as a subgroup of a house, and these are held together during the calculation engine when assigned to one of the three phases, for example. You can also load in your own GIS network data if using our enterprise version, or load in networks from a cloud storage area from your own designs and your team's designs as well. So here's one I created earlier. This is a medium-sized suburban sort of network. And once you've set up all the parameters for your design, you just click the Run Assessment button, and all of the behaviors of the network is calculated for you. As you can see, there are a variety of colored numbers that are displayed on the network. These are all the results, and you can see in the results pane which result is which. So currently we're displaying maximum volt drop in red, but we've got a huge variety of results that are automatically calculated by the tool, such as volt drop, volt rise, current, utilization, and impedance. It also automatically calculates whether the values are over the recommended limits for a network, so it's really easy to tell whether your network is okay or not. You can also filter results by summer, winter, or overall worst case, as Visnet design models summer and winter in full detail in order to capture all the potential worst case scenarios for a network. And you can display all of the different results as it's customizable as you like when you're building a model. So what is the difference between the Debbie method and ADMD? So we've built a network in Visnet design, which is quite similar to the one that I was just up in the video. So this network contains 131 houses, including four blocks of flats. 19 of these houses have a 7 kilowatt EV charger. These are the ones marked in green, and 4 shops marked in yellow. The model has been built in Visnet design so that the transformer and cable models are identical between the 3 scenarios. You can build ADMD models in Visnet design, and including a mix of different property types. It's very customizable in that way. But all 3 models have been built in Visnet design just so it's the only difference is in what is being modeled. There aren't any resistance differences, for example. It's just about how the customer demand is being modeled. So as there are 2 main effects that are the difference between the Debbie approach and the ADMD approach, there are 3 models that look at 3 scenarios that are going to be compared in this circumstance. So scenario A, the top scenario, is the full Debbie approach, where each customer is defined by this daily profile, and it uses Debbie's model of diversity. The second model is an ADMD, so it's removing Debbie's model of diversity, but it's keeping that half-hourly profile for each customer. So this model will take into account time of day demand coincidences. And the final model is just assigning each customer a flat ADMD for each property type. And each property type has been assigned a similar size so that at high customer numbers, they're equally comparable. So what are the results of this comparison? So I'm going to talk through 4 key points on the network. The first of these is the transformer maximum demand. And you can see here that the figure for the full ADMD approach is by far the highest. It in fact overloads this 315 kVA transformer slightly. This is because the full ADMD approach assumes that the maximum demand of all of the houses, all of the EVs, and all of the shops is at the same time of day. Whereas real life data will tell you that this isn't exactly the case. Shops tend to have a daytime or morning maximum demand peak. Houses UK houses, I will hasten to add for this the purposes of this illustration, UK houses have an early evening demand peak and EVs a late evening demand peak. So there's a slightly non-coincidence of demand that means the full ADMD approach is overestimating the total demand here. And you can see this by comparing it to the half-hourly ADMD profile. The result here is about 50 kVA lower than the full ADMD approach. So you can see the immediate headroom that opens up on that transformer by properly accounting for this effect. The W approach again is slightly lower than this because it accounts for the full approach of diversity between the customer types as well. Similarly, for the first leg of the maximum current in this network, you can see a very similar effect. The full ADMD approach again is overestimating the demand, as it's assuming all the maximum demands are happening at the same time. And this overestimates it by about 100 amps. And you can see the difference between the two ADMD approaches. The W approach gives you a very similar current to the half-hourly ADMD approach. So again, the full ADMD is a way overestimating the demand. The third point of interest is right on the other end of the network, the service cable current. So you can see here that the full ADMD approach has a service cable current expected to be 18.7 amps. This just comes from the straight 1.5 kilowatt model for the house, plus the 2.8 model for the EV, added together, converted to amps. All nice and straightforward. The half-hourly ADMD approach is very similar, except it accounts for the slight non-coincidence of maximum demand. The EV demand is still high at the time of maximum house demand and vice versa, but they're not quite got at their maximum at the same time, which is why this middle model is slightly lower. There is, however, a big difference in how W has modeled the service cable current. So the two ADMD approaches are using this fully diversified demand model to estimate the service cable current here, whereas W has modeled the demand at the from this house and from this EV on the service cable at the one customer diversity level. So this results in, for this service cable, W models the house at about 2.5 kilowatts instead, and the EV at close to its maximum of 7 kilowatts. And this adds up to a total of 35 amps, which is much closer to what you'd expect as the maximum service cable demand for a house and a 7 kilowatt EV charger. So you can see that W, with its dynamic approach to accounting for levels of diversity, is giving you a much more accurate level of current at all levels of the network. And you can see the overall effect of this in the final result, which is the point of maximum volt drop on the network. So you can see the knock-on effect of the overestimated currents from the ADMD approach spilling over into the maximum volt drop modeled in this approach. You can see here quite high volt drop of 4.07 for this network is high because the currents have been overestimated. The other two methods have a much lower volt drop. The half-hourly ADMD is much lower at 2.88. W, with its more accurate currents modeled all the way down the network, and particularly its slightly higher currents towards the service cable end of the network as the network branches out, has a slightly higher and most accurate volt drop of 3.27%. So what does this essentially mean? What's the takeaway from this? Well, if you're a network planner and you wanted to add some new EVs or DERs to this network, if you were looking at this with the ADMD approach, it would say that the transformers are already overloaded. You can't fit any more EVs on this network. If you look at the half-hourly ADMD approach, you can fit 34 more EVs before you blow the fuse on the first leg of the current before you run out of space on the network, as that is the limiting factor for this for that approach. And the debut approach says you can fit in 60 additional EVs before the network overloads. So you can really see the benefit that could be given by accurately modeling the demand across the network. It brings visibility to how much potential extra headroom you have on your networks and what the benefits that model this network-wide accuracy can get. So all of my examples so far I've mentioned they are UK examples, although the principles are equally applicable to Australia, New Zealand, and elsewhere. But so how would we generate some debut profiles to make some more accurate Australian and New Zealand and other networks? So ideally, the focus would be on the profiles that are most different in shape to UK profiles. For example, this could be a domestic summer profile to account for air conditioner use, or I don't know how much you guys use heat pumps, but a different shape for those to reflect the different temperature difference. But it's relatively easy to create new debut profiles. All we need is an amount of smart meter data, and as Australia in particular has pretty high levels of smart meter penetration, this is relatively straightforward. So we've got a well-established process for generating profiles from smart meter data. At a minimum, we'd be looking at needing about a year's worth of data for 30 to 50 customers. Now produce a sort of like lowest acceptable quality for profiles, but better, more accurate profiles can be obtained from larger amounts of data. So this smart meter data is subjected to Monte Carlo analysis to look at the statistics of the customer's maximum demand for each half hour. And these extracted statistics are used to create the customer profiles. So what do the profiles actually look like? I've been talking about these a lot. Let's take a look at some examples. So these are some illustrations of some UK profiles that are available in the tool. On the left is a domestic winter profile for a gas heated property. So you can see that as a result of the statistical approach, we're left with the profile that gives you a very general approach of what behavior would be typically expected. And it ends up being quite intuitive when you look at it. It's much easier to understand than the first graph I showed. You can see here low nighttime demand when stuff's on standby, evening peak as everyone's cooking, lower but not unnoticeable demand during the day. Similarly, we've also got a profile for storage heated properties with quite a similar daytime demand if you were to adjust the y-axis to a similar level, but a high nighttime demand as the storage heating is filled back up when electricity is cheaper during the night. We've also got quite a wide variety of profiles for commercial and industrial properties. I've included a shop profile here as an illustration, but there's also offices, churches, schools, various different levels of medium, light, medium, and industry that can be connected at low voltage as well. And more importantly, we have some DER profiles as well, and these are some examples of these. So we've got a dedicated winter heat pump model. You can see with the relatively high base load and a higher demand during the day as everyone's awake. We've also got a dedicated EV charge point model. You can see the evening peak demand here as everyone's returned home from school, work, and various evening activities, the maximum demand peak in the late evening. And we've also got generator profiles as well. This example is a summer photovoltaic array. And you can see here because this is a generator, it's upside down. As this isn't demand, it's generation. And all of these profiles are built from real life data. So they are this isn't something we just completely made up. These are real life profiles that actually represent how these customers behave. We've also got vehicle to grid profiles, time of use tariffs, and all sorts of other useful models for different upcoming technologies. So just a quick summary. So DEBU produces a realistic worst-case model of the network using a very well-established algorithm that's been tested, proven by data. It models time of day and diversity on all network sections with a great deal of accuracy, which leads to, in turn, to a much better view of the available headroom for current, demand, and volt drop across your network. And it also contains dedicated models for DERs. And I'll now hand you over to David to talk about planning for the future. Thank you.
Thank you, Catherine. So just to follow on all the work that Catherine's talked about around designing the network and looking at how we're connecting new loads now. And I thought I'd take the opportunity just to give a slight overview on some of the work we've been doing, looking at how that might change in the future. And so you can go to the next slide. So obviously we're all aware that we're going to have we're having more embedded generation, uptake in electric vehicles, and it's all changing the demand on the system. Alongside that, though, we've also got the growth in flexibility markets and how we adjust the way consumers may respond to signals and change their demand. So all of the analysis that we talked about earlier talked about diversity and how we need to understand diverse range of customers. And here are some findings we've had from recent projects looking at how customers might respond to a price signal. So this is a collection of batteries, all within the same local area, and all responded to a pricing signal sent by the network to, in this case, to try and reduce the or consume excess generation in the network during the summer. So we have big swings in our charging and discharging profiles, which go against some of the analysis as we would have done earlier in terms of the diversified profiles. So using some of this analysis and the understanding of uptake of different technologies, it's important for in this case, the NSPs, so for yourself, or distribution networks in the UK, to understand how this might impact their network capacity, but also understand how they can make use of it in the future. So if you go to the next slide. So we recently completed a project for TAS networks, and this was trying to understand how much capacity was needed to accommodate growth in solar PV and electric vehicle uptake. So this project, carried out a couple of years ago now, was all around trying to understand, based on the projected uptakes, how much would the network have to invest to accommodate the electric vehicle profiles as Cass presented earlier. But then also, how might you be able to incentivize customers to shift some of that demand? So rather than it being charging at 5 p.m, can you get them to charge overnight? And actually, how much demand do you need to change to significantly reduce the cost of expenditure of the network? So we utilize our transform model, which is a scenario analysis tool that we've developed that allows you to run various scenarios for different uptakes of technology and investigate different costing models around both the cost of solutions, so how much does it cost to replace a transformer, upgrade a circuit, but also how much we can incentivize customers to shift their charging to other times of day and save on network investment. And so I will get straight to quick high-level overview of the findings. Next slide, please. So this slide presents some of the outputs, and I should add this paper was presented at a CGRE symposium, so there's a lot more detail behind this that is available and can be provided. So basically, as we show if you can try and get customers to shift onto a time of use tariff, so that's shifting their charging to be overnight, taking it away from that system peak, there's a significant investment saving for the network. So now we're in a world where we're going to have to model based on typical usage patterns and also start considering alternative usage patterns and developing profiles based on how people might use their vehicles in the future and how they might respond to signals. So being able to take out some of that diversity and include different assumptions to come up with that as an output. And so here you can see significant investment saving, the different uptakes, and the 4 different scenarios on the side of the 4 different technology uptake scenarios to show that in all cases there is some network investment saving. Thank you. I think I'll hand over to Yugandra, who's going to wrap everything and bring it all together.
Thank you. Thanks, Catherine, and thanks, David. Look, in Australia, just to give you, you all know that Australia, we follow the AS3000, and it has 4 methods. So it has the methods like saying calculation, assessment, measurement, and limitation. So it specifies 4 methods of calculating the diversity and demand. And I'm hearing these days that, the AS3000 has not gone to 100%, all the profiles. Although it has under the load table, it has EVs, but then it classifies EVs based on, say 5 dwellings or, more than that. And it says if it is up to 5 dwellings, just take the 100% load, that kind of the static definition is there still. So what happens is that in EV, I've seen people using 2 methods like calculation and limitation. So they're saying, okay, we have been given 63 amps with 80 amps fuse. Now, if we are using 7 kilowatt, that means we are this 32 amps load, then we have to add this 32 as it is, like for a smaller EV things. And the second method can be limitations that we can limit the load. But however, this will require further because the things are much more complex in terms of generation, time shifting through storage, and the market incentives, the flexibility market, which time of use tariff or demand side participation. So it is the VPPs, you name it. So it is more complex than what we can use the table as it is. You would have seen that in your design, in the planning design manuals, it will say typical, residential, of course, from subdivision to subdivision, and they are reviewed after a few years, but generally 5-6 kVA per customer. But in the DER or CR risk scenarios, we need to really understand all the complexity, which David was explaining, and see how we can model, take advantage of these profiles in building the diversity, in calculating the demand and forecasting for future. And which on the right side, there's another, EV profile I'm saying, which is used for ISP 2024 draft. And this is a kind of, how these profiles are actually embedded into the tool. So the planners can use it. Next slide, please. So look, before we go to the Q&A very quickly, what I can say is that EA technology in Australia and the UK, they have been working in this area for many, many years, and they understand, what are the current best practices are in Australia and UK and what the challenges ahead. And then EA technology, as you saw the video for VisNet design, that have developed a tool based on Dayview method, and which can actually model the LV circuits. This is actually has become more critical in terms of the LV visibility, I mean, in Australia also we are talking of dynamic operating envelope, but we need the data. We need to understand either from calculation or assessment or measurement or smart, we need to understand what is the load, non-DER load, and how the DER will behave in terms of the time profile. And that will also, these tools can help us to optimize the connection designs and even generating the bill of materials and estimations for that. Next slide. Okay, so I'll hand over to Ian now to conduct the Q&A session.
So good morning or good evening, everyone, depending on where you are. Thank you very much for staying with us during this presentation. My thanks to Catherine and David and Ugendra for speaking to us. If you could put your cameras on, and then we'll go through some of the questions that people have recorded in the chat for your responses. So if you have any additional questions, please feel free to add them into the chat, and we'll get through a few of the questions over the next few minutes. So the first question I'm going to pass through to Catherine. I think has been you answered in your presentation, but can you include PV inputs from homes into the model?
Yes, you can. Say this won't be the direct smart meter data from the property itself, but if you know your the maximum expected output of your PV array, this size can be put into the model. Alternatively, if it's the DNSP that's working with the tool and they have the data already stored in their databases, this can be directly brought through.
Thank you very much, Catherine. So is the next question I'd like to ask listed here is, so is it fair to assume that Debut does not use a normal distribution for electric vehicles across the 24-hour period, but rather a typical EV charging profile? Could you perhaps expand a little on the kind of some of the data behind the EV profiles that we use?
Of course. So the EV profile came from a project that we did here at EA Technology in partnership with one of the UK network operators, using a trial of several hundred EV owners running with smart meters attached to their chargers, and we collected the data for several. Can't remember exactly how long off the top of my head, but it was a couple of years. We then analysed this data and verified that in each half-hour profile, the demand remained normally distributed and therefore was compatible with the Debut model. And so this approach means that the profile of the EV that's built into the model is a typical shape of demand across the day for a standard EV owner. So it contains quite a lot of diversity, this profile, because it's accounting for like variations in how charged the battery is from day to day, because that causes a lot of variation in the data, how often people plug their chargers in, and so forth. So it isn't for an individual EV, but it's in general charging behavior.
Catherine, just wanted to ask you or add into that. Is that if we are also generating in Australia some profiles like EV Grid project and other things, and there is a difference between how many miles you drive, in Australia or UK. So basically, I'm saying the existing profiles from UK can be used and they can be scaled up to the travel thing, and also the Australian profiles, which are coming now more and more, can be used in the model. Is that correct?
We're more than happy to work with network operators and other data providers to add in more Australian accurate EV profiles into the model. Absolutely.
Thank you.
Certainly, thank you very much, Catherine and Ugendra there. So there's a couple of questions around verification against existing network measurements and real current measurements. And I think there's one of those that against the equivalent smart meter data from customers, and accuracy there. Kath, if you'd like to ask that, to speak to that point, and then I'm happy to describe some results that we've seen where we've been installing LV monitors at substations and comparing against the data that we've received from those.
So there's been a recent project in the UK that's been using smart meter data to predict the demand of neighbouring properties, and the debut approach was more accurate than using neighbouring smart meter data to predict network demand.
So the results so far is that it's pretty good. It's not perfect. We're aware of that. It's no model is perfect, but it's pretty good. And against real current measurements, so we at EA Technology produce a hub, part of our VisNet smart grid technologies that monitors LV networks distribution substations, and we've compared the data from some of these that we've had installed for a couple of years against the results from the debut engine. And what we have to do once we've taken that measured data and we've cleansed it and effectively taken the 90th percentile equivalent point on the probability curve that we would with the debut assessment, actually we have seen that debut using the profiles standard profiles we have built into the tool is slightly conservative. It actually overestimates the demand very slightly, and so the networks in the UK using it have confidence that there is a little bit more capacity available than the debut model is telling them. We've also been working with a couple of those networks and some more recent data to say, actually, can we improve the standard profiles that we use? Because due to the number of energy efficiency measures in the UK, actually the demand is dropping over time to be able to bring that result very slightly closer. So we have done some testing and we've got some results, and I think to say again, it's pretty good. It's not perfect. No model ever will be, but it's pretty good. The next question through in the list is one talking about diversity destroying events. So if there's a coincident event where in this case there's a loss of PV along with an increase in peak demand. So Catherine, could you talk how you could potentially model what the peak demand could be on a network if this diversity was removed?
Sure. Right. So if you model this example scenario in debut, you could first design the regular scenario with all of your aircon load, for example, having the diversity included, and all of your PV being set to its expected maximum output. You could then run a second scenario with all of the aircon set to no diversity, because you can turn the diversity off for each model in VisNet design. And you can, and then if you were to turn all the PV down to zero demand, then you could quite easily and quickly model this potential scenario.
So thank you, Catherine. It's something that we see in the UK, where there are commercial tariffs that are driving the behaviour of certain flexible demands on the network, which is reducing the diversity in some areas, and it is a concern for the networks here. And so it's something that we are definitely keen to model and to help people understand, and certainly we think it's easier and better in the tool that we have than potentially an ADMD approach, just showing a single peak value for the day. Thank you. So there are some more questions coming in. So if you do have more questions, please keep them coming. We've got time for a couple more. We'll go through. So the next one is talking about the results. So are the final results based on the percentile threshold from multiple model runs, or just one combination of debut profiles? Catherine, if you could respond to that, please.
There are essentially two models that are run for each season in debut. One is the maximum demand, minimum generation scenario, and in that model, it's essentially looking for the maximum demand, maximum current, maximum volt drop across all the network. The other scenario is the converse. It's the maximum generation, minimum demand scenario, and this is the run that gets the volt rise and other issues when generation is dominant on the network.
Thank you, Catherine. So the next question I'd like to ask, so can debut tease out different profiles for different types of customers? For example, bars or restaurants versus a post office.
We do have a profile which is much more a pub bar sort of profile. It's got a more evening peak, and the shop profile has got a more daytime peak. Debut itself doesn't create the profiles. That's something we, our team at EA Technology will do. But given the data, we're more than happy to look into developing custom profiles, more varied sets of profiles, if the data is available, to develop these models.
Thank you. And certainly with enterprise customers where we're integrated with a network, we can take in a specific set of half-hourly values for each individual property into building the model, and can run analysis with that. So if you have model measured data in that sense, we can bring that in specifically for different customers. There are time, I think, for perhaps just one or two more questions, and before we close. So one to ask from Corinne. So is the weather forecasting being considered in these models? So I'll ask Kath if you could take that first, and then potentially David if there's that in some of our forward-thinking analysis.
It isn't directly being considered, but because the data that's been taken in to develop the profiles, this is why we prefer many years worth of data as opposed to just a short period. This allows us to capture a wide variety of different weather conditions to figure out where the realistic worst case scenario is. We've also done some weather normalizing of real life monitoring data to create weather normalized worst case profiles from our VisNet monitoring data at a feeder and transformer level as well.
Thank you. And I guess looking at it from into the future is something that we are incorporating into some of our analysis, looking at network reliability. So bringing understanding of not only how does the demand affect how does weather affect the demand, but also how does weather start to have impact on asset reliability and outage conditions, carrying analysis out in that space. So it's an area we are focusing on, starting to develop some projects to look into that.
Cool. Thank you, Catherine and David. And one last question. So when we've indicated maximum volt drop within the tool, does the tool also show voltage rise to enable your total voltage regulation parameter?
Absolutely, yes. When it calculates that minimum demand, maximum generation run that I referred to briefly earlier, it does calculate the volt rise on the network. It does also do this during the maximum demand run to account for the effects of volt rise due to unbalance across the 3 phases, but primarily this will be due to generation. And you can see the split of these 2 effects in the tool. There is a dedicated volt rise section in the results pane, so you can isolate this result in particular.
Thank you very much, Catherine. So I'd like to thank everyone. I'm going to close the Q&A here. There are a couple of questions we've not been able to answer, but thank you very much. We'll definitely come back to those over email, and welcome the opportunity to carry on the conversation with you. I'd like to thank our speakers. So thank you, Catherine and David and Ugendra. And to thank all of you for giving up your time to come and listen to us today. We hope it's been a very useful and interesting discussion for you. So thank you very much and have a good day.
Thank you. Thank you.
Thank you, everyone.
Thank you, everyone.